Hi, this is Theo, and this is the rolling roller coaster problem. So, we've seen this kind of problem before, but it's been a little bit more simplified. Um, so, we have a ball of mass m and radius lowercase r, and it is rolling, not sliding, down a roller coaster, and it goes around this loop of radius capital R, and it starts at a height h, which we're going to find, and we're kind of looking at this point A. Point A is where it's at the very top of the loop. And we're also given that the for a ball like this, the moment of inertia is directly proportional to its mass times the square of its radius. And the constant of proportionality there, we're calling B. Okay, so part A, we're asked to find the minimum speed of the ball such that it reaches A and just barely keeps, it doesn't fall though, it like keeps going around the loop, but it kind of barely gets past A. And if it's just barely getting past A, basically what we're saying is that the centripetal acceleration, because it's, this is a centripetal situation, the centripetal acceleration is only going to be influenced by gravity. In other words, there's no normal force. So, our free body diagram looks like this. The only force acting on it here is going to be gravity. So therefore, if we take a sum of forces, I'll define my axes. So that's a negative y. I don't think I'm actually going to need the x-axis here, but yeah, that's negative y. And then acceleration is also going to be negative. Of course, it's, being pulled down. Okay? And because this is centripetal acceleration, right, because this is going directly in the same direction as centripetal force, we can substitute A for v squared over r, and do some cancellations, cancel out the negative m, g equals v squared over r, v squared equals gr, and then we can say v equals square root of, oh my god, I'm sorry, I got that. There's actually an important distinction. The circle that we're talking about with the centripetal acceleration is the larger circle with a capital R radius, which is actually important in this case because there is a lowercase r. So there we go. V equals square root of gr. So that is the minimum speed necessary. Okay, so I'm going to keep that up there. We're going to need that for the second part, which is finding the minimum height that we need to release the ball from for it to attain this minimum speed and barely get around the loop. So at first this might seem exactly the same as other roller coaster problems, but this is kind of where the rotation comes into play, because we solve this with energy, and we got to remember that there's some rotational energy as well, because the ball is rolling. Okay, so I'll define href equals 0 to kind of be at the bottom of the loop, such that here the y component is actually equal to this variable h, which will make it easier for us. So the energy at the beginning, the ball is at rest, there is no kinetic energy at all, so the only energy is potential. And then at this point A, we still have potential. In fact, the height here is going to be equal to the diameter of the loop, which is 2r. Right, large r because it's the large loop. And then we've also got some linear kinetic energy. And now we've also got some rotational kinetic energy. And basically we just do some algebra and we're going to solve for this h. Okay, so I'm going to kind of use this square root of gr and definition of rotation to boil all this down to kind of get rid of the velocity stuff. So v squared equals gr. I equals bmr squared. And then omega, because we're talking about the rotation of the little ball, well, we know that omega is linear velocity divided by r. In this case, it's a lowercase r because we're talking about the rotation of the little ball, not its rotation around the big circle. and that will solve. You can see we're going to have a little bit more to do here, but well, actually, I'll just combine these like terms. Turn into 5/2. Okay, so here, this turns into, these lowercase r squareds are going to cancel out. I'm going to get bmv squared, and then we're going to sub v back in. V squared equals g capital R. And, oh yeah, I forgot my m. mg capital R. And now to find h, we can just divide both sides by mg. So h equals 5/2 r plus 1/2 er. So it varies with both the radius and a little bit with respect to b. I'm going to keep that equation up here, but I'm just going to erase this with more space. Okay, so next we are given data from an experiment where we basically know we somehow got the constants for different objects, such as a hollow sphere, solid sphere, I think hollow cylinder, solid cylinder. Doesn't really matter, but all I need to know is they have different b values, and they measured the height h that was required to get it to just pass A. So we're going to graph h versus b. I'm going to do the best I can with this whiteboard, but I also did it on paper, so I'll be able to find the slope more accurately, or at least more precisely. Okay, so h versus b, so that makes b our x-axis, and h our y-axis. Let's actually find this unit. So b, so moment of inertia is in kilogram meter squared. So mr squared actually already takes care of all those units, so b is unitless. So we can just leave it like that. And let's go ahead and, yeah. So graphing b versus h, our x-axis goes from 0.4 to 1.0. I'm just going to start at 0, so it's a little bit kind of more intuitive. Make this 1.0, and then I'll just divide it into like 5 things, I think. Okay, and then our h-axis goes from 1.08 to 1.2. I'm going to start the graph at around 1 because there's a lot of extra space otherwise. So I'll just make this 1 kind of arbitrarily. And then we're going up to 1.2. Good enough. Okay, so let's graph all these points. All right, b equals 0.4. Oh, I got to label my axis here. So b equals 0.4, h is 1.08. B is 0.67, h is 1.13. That's 0.7. Like there. B is 0.5, h is 1.1 exactly. 0.5 and 1.1. Finally, b is 1 and h is 1.2. So that's kind of at my edge. And then we're going to draw a straight line, kind of a line of best fit, and see if we can use that to find this constant capital R. Okay, that was terrible, but anyway, we got the idea. Again, I also found this on paper, so I have kind of a more accurate slope, and this is what I found the slope to be equal to. Let me just find it. Okay, I found my delta y to be exactly equal to 0.2, and my delta x to be equal to 1.0, and that gives us a slope of 0.2. Okay, so here, if we're taking r as a constant, then h only varies with b for the second term. In other words, if we kind of ignore this 5/2 r because it's constant, then we can say that h over b roughly equals 1/2 r. Of course, this is not really equal at all. There is a constant component, but we're just going to ignore that for now because we're just considering the slope. So the slope is 0.2 equals 1/2 r. So therefore r equals 0.4, and that is in meters because h is meters, b is unitless. So that'll give us our value for r. Okay, great. Oh, I think I skipped a step. Sorry, that was actually part E. Oops. Part D asks if h is 1.16, then find b. So I'll try and kind of draw it out here. When I did this on paper, I got a value of like 0.81 for b. Yeah, kind of an arbitrary value, but I guess testing our linear graph skills. But yeah, so I guess you could say like h of 0.81 equals 1.16. Yeah. Okay, and then the last question, that was E. The last question is kind of weird, and it's different from what we've seen before. So at the beginning, there was an assumption made that r, lowercase r, in other words, the radius of the ball, was significantly less than capital R, in other words, the radius of this. And now we're going to say, if we didn't make that assumption, how does the minimum required height change? So let's take a look at this. In order to find our minimum required height, we kind of use this capital R. But the way that we got that is we used kind of a centripetal acceleration model where we used a v squared over r. And that equation, basically the r that you're plugging in here is the radius of, the radius of the circle, from the perspective of the center of mass. So if this radius was super big, then the center of mass is significantly, or the radius from the center of mass, in other words, this distance, is significantly different from capital R. And that distance is significantly less than capital R. In other words, kind of when we boil it back down to here, the capital R in general, the radius of our rotation, is going to be lower. And so if R, right, if our realized capital R, the real radius of kind of our circular motion, is less than the original, well, h is directly proportional to r, so we can say that the resulting height for a given constant mass, radius, is going to be less than the height if we assume that the radius is significantly less than the radius of the loop. So yeah, just to summarize, initially we found that the minimum speed required to kind of go past point A but not fall was square root of gr, and then we used that to find the minimum height required, including rotation, which we found to be 5 halves r plus 1/2 br given b, and then we were given some experimental data. We graphed h versus b, did a kind of linear approximation there, found a value of b given h. Then we estimated r based on the slope, and we found it to be 0.4 meters. And then finally we said, if we kind of throw away one of our assumptions, how does the calculated height change? Or not, that's actually not true. Not the calculated height, but the actual height required to get past A. How does the actual height change? And it's going to be less because the great radius is also less. So yeah, that's about it. Thanks for watching.